and then we can take a few questions. So please go ahead. Thank you.
Can you say my correct screen?
Yes, we can.
Okay. Hi, everyone. Today, I'm going to talk about our work, energy-based model for continual learning. This is a joint work with Yilun, Gido, and Igor. So as humans, we interact with the world, learning new skills, get feedback from others, and consistently improve ourselves. As shown in these videos, the baby first learns to crawl on the floor, and then they learn to stand up and walk when they get older. And after that, they learn more sophisticated skills, such as opening the door. In addition to learning these skills, humans can also transfer what we learned from the past to solve new tasks. However, it is very challenging for models to continually learn new knowledge without forgetting the old knowledge. And in our work, we will teach models to continually learn new tasks. And taking the classification task on MNIST as an example, there are 10 classes in the dataset. And we separate the dataset into 5 subsets. So each subset has 2 classes. And in this work, we will focus on the class incremental learning setting, which is one of the most challenging continual learning settings. And in this setting, the model needs to do classification from all scene classes. So the biggest challenge in continual learning is the catastrophic forgetting problem. As shown in this first figure, we can see the accuracy of task 1 is close to 1 when we train the model on the first task. However, it suddenly drops to 0.5 when we train the model on the second task. And similarly, in this second figure, the performance of the second task drops when we start training the third task. So most existing continual learning methods use the softmax-based classifier to do classification. However, we found that the softmax normalization is one of the main reasons that cause catastrophic forgetting. And here is an example. This one is the results generated by the soft-based classifier. And after retraining the 5th task, the last task, the model is supposed to predict all scene classes, which is from 1 to 10. But for SBC, it only predicts the most recently seen class, 9 and 10, which means it forgets previous classes. And this is a result generated by our model. We can say it can predict all scene classes. So in this work, we use energy-based model to solve the continual learning tasks. And here is the definition of energy-based model. And the energy-based model the probability of the data point X using this equation. And the E is the energy function. It is a neural network and is trained to output an energy scalar. And Z is the partition function for normalization. So to do classification tasks, we model this conditional probability of the label Y given data X. And we use this contrastive divergence training objective to train our model. Here in this training objective, there's a 1 positive pair and a 1 negative pair. So the positive pair contains an image and its ground truth class label. And the negative pair contains the image and a random class label. So the goal here is to minimize the energy of the positive pair and maximize the energy of the negative pair. And this is a comparison of the model architecture of the softmax-based classifier and our energy-based models. So in our energy-based model, we take both the image and label Y as input and output their energy. And this architecture is very flexible. It can allows us to combine the information from the image and label in many different ways. And during inference, we feed each class label Y to the energy function and compute its energy score with the image. And the prediction is the class label that has the lowest energy. And here is the comparisons of energy-based model and baselines on 4 different data sets. So we first compare the basic version of energy-based model and softmax-based classifier. And for fair comparisons, we control they have similar number of model parameters. And here we can say the energy-based model is much better than softmax-based classifier on different data sets. We then compare the energy-based model with other continual learning methods, and these methods propose different ways to prevent forgetting previous tasks, but they do not use replay buffers. And the energy-based model is still better than these methods. And this figure shows the classification accuracy when we sequentially train the model on different tasks. For example, the blue lines, this one and this one, are the accuracy of task 1. For the softmax-based classifier, its accuracy is high when we train the model on task 1, but the accuracy drops when we train the model on other tasks. But for energy-based model, we can say the accuracy of the task 1 doesn't drop a lot when we train new tasks. And we further compare the proposed method with continual learning method that use replay buffers. And this means they save some data from previous task and they train the old data and the new data together. And methods use this replay, they usually perform much better than methods without using replay. But we found that our energy-based model can be combined with this method, for example, the exact replay, and it's achieve better performance. We also did some experiment to investigate why energy-based model can mitigate catastrophic forgetting. So one hypothesis is the training objective. Here is the proposed contrastive divergence training objective. We compare this training objective and another 2 baselines. So in the first baseline, all negative thing, the negative classes here are all the classes seen so far. And the second baseline, all negative batch. So the negative classes are all classes in the current batch. And the last one is the proposed training objective, which only sample a single negative pair in the current training batch, and it achieves the best performance here. So the training objective is helpful for continual learning. And here we show that this training objective can also be applied to existing continual learning methods. And these are the result of the baseline methods that use their original training objective and our modified training objective. And we can say, like, compare with the original training objective, the contrastive divergence training objective can improve their performance. But it's still slightly worse than our energy-based model here. And this is the classification accuracy when we sequentially train the model on different tasks. And this is a curve that after we modify the training objective, and we can say it makes the accuracy of previous tasks drops much slower than the original training objective. And this is our energy-based model. So this result shows that both the training objective and the energy-based model architecture helps continual learning. And these are the predicted label distribution. As we have shown, like energy-based model can predict all thin classes, but softmax-based classifier only predict the most recent classes. So we have shown the result on the boundary-aware setting, which means there are clear task boundaries. In this setting, the model is first trained on the first task and then move to the second task and so on. However, this is more realistic for tasks to change dynamically, and the model don't know the task boundaries. So we also compare our method and baselines on this boundary-free setting. So in this setting, the models learn in a streaming fashion and the data distribution sequentially changed. For example, in this figure, the percentage of ones gradually decrease while the percentage of twos gradually increase during training. And here are the result of energy-based model and baselines on this boundary-free setting. Our energy-based model is still better here. So to conclude, there are 3 main contributions in this paper. First, we propose to use energy-based model for continual learning. Energy-based model can be naturally applied to solve boundary-free setting and class incremental learning setting. And second, we propose a simple but efficient energy-based training objective. It can be broadly applied to different types of models and significantly boost their performance. And finally, we use energy-based model as a building block for continual learning. It can be combined with existing continual learning methods, such as replay. Thank you very much.
Are there any questions? Please come to the mic if you have a question.
Thank you for the talk. So I have a question. It looks like it's a conditional energy-based model where you are just predicting over the labels. So couldn't you do exact maximum likelihood training? It was not clear, like the functional form of your model looks like a softmax classifier, and you mentioned that the main difference seems to be the training objective. So if you did exact MLE training, wouldn't they be the same?
Sorry, you mean like use image? Sorry, can you repeat your question?
Yeah, so you're sampling a random Y minus just one sample, but you could sum over all of them. Like you've got Z upstairs, right? That's a tractable computation because Y is finite and small. So you can just take gradients and do MLE training. So what happens when you do that?
You mean like take all the class labels here?
Yes.
It performed very bad here.
Yes. Okay. So why is that? So why is the nominally the optimal thing apparently much worse?
Oh, I think the thing here, when we only sample a single negative, we actually decrease the probability or increase the energy of a single negative pair. So we don't compress the probability of other classes. And for the method like soft mass-based classifier or this one, like have all the negative pairs, they actually decrease the probability of all the rest negative labels. And includes the labels that from previous task, and that makes the model easier to forget previous tasks because they purposely, make their.
Oh, I see. So like if I'm at the end of training, I see a digit 0, or let's say a digit 1, I'm gonna call that a negative, even though it's not a negative in that context. So there's a hidden variable that you're ignoring, and that conflates everything. So if you do stochastic training, it works better.
Yeah.
Okay. Okay. Thank you.
Any other questions? Okay, then let's thank our speaker again. And we will move to the next presentation. So this is Continual Learning with Foundation Models, an empirical study of latent replay. And Oleski, Oleski